In this video, we're going to talk about logarithms, and we're going to talk about logarithms in terms of inverses of exponential functions. What we've learned so far is with our exponential functions, it's in the form y equals bx, or y equals a times b raised to the x. Just as you have inverses with addition is going to be subtraction, the inverse of multiplication is division, that kind of opposite step, like the inverse of something being squared is the square root. With any type of exponential equation, we can use what's called a logarithm as its inverse. So as you can see here, a logarithm is a function with the general form log with this little b in the subscript, x, and that's going to equal y. So another way to look at it is log, here's our base, here's our solution, and it's equal to our exponent. So where does that come from? If I wrote a simple equation here, y equals 3 to the x, if I were to take the log or inverse of that function, when I take the inverse, I'm going to switch my x and y. X equals 3 to the y. And I want to isolate y, so I'm going to take what's called the log of both sides. Log, in this case, it's going to be base 3. And on this side also, I'm going to have log base 3, and that's going to be 3y. So let me rewrite this. And when you take the inverse of a function, all right, over an exponential function, it's the opposite. So when I have my exponential here of this base, log 3 of 3, this is being eliminated. So what you would be left with is log base 3 of x equals y. Right? It's our new function. Let's take a look at a few examples of how to switch between logarithmic and exponential form. If this was our exponential form, x equals by, similar to what we have here, x equals 3y, I can rewrite this as log with our base. Remember, our base was 3. Here is our solution, right? That was our solution. And y is the exponent to that exponential. So it's kind of helpful to remember this as log. What's the base? What was our solution? What was the exponent? The goal with our logarithms is to solve for the exponents of our functions. Let's take a look at a few examples. If I have 100 equals 10 squared, we can agree that 10 times 10 does equal 100. I can rewrite this in logarithmic form by taking the log base 10 of both sides. Now if I do it to the left side, nothing is canceled. If I do it to the right, it's base 10 of 10, that was our base, that gets eliminated, and you're only left with that exponent of 2. So log base 10 of 100 is going to equal 2. In this example, if this is our solution, here's our base, here's our exponent, log base 3 of our solution equals the exponent. Let's take a look at a few examples. I know that this 36 is our solution, 6 is our base, and this is our exponent. So I could write this as the log of base 6 of our solution 36 is going to equal our exponent of 2. Log base 2/3, our solution was 27, 8 over 27, it's going to equal our exponent of 3. Log base 3, 1 is going to equal 0. Anytime you have the log of any base that's a solution of 1, it's going to have an exponent of 0. And here we're going to have a log base 4, solution 4 is going to equal our exponent of 1. Anytime you have the same base and same solution, right? In this case both 4, it's going to equal 1. Hence why when we go back up here, that was eliminated because this was 1. Now, in continuing our logarithmic functions as inverses guided notes, we're going to talk about what is a common logarithm. A common logarithm is a logarithm with base 10. You can write these logarithms without showing the base 10 and simply as log of x. It's assumed that that has a base of 10, unlike these examples where you had different bases like base 6, base 2/3, base 3, and base 4 in a logarithm. You don't have to write 10 here. Sometimes I've seen it there, but you don't necessarily need to write it. So how do we evaluate logarithms? Right? You can find a common base when evaluating a logarithm. So what is the value of log base 8, 32? Remember, our goal is to solve for the exponents, right? We don't know the exponent in this exponential function. So first we're going to take our logarithmic equation, our expression here, we're going to set it equal to x. Remember, that is our exponent. And we're going to change it into exponential form. Right? So here's our solution equals the base of 8 raised to some exponent. Right? I'm just following along with here's our logarithmic form. Here was our solution, here's the base, what is the exponent? This is now in exponential form. So looking at this, 8 and 32 do have a common base. I could write 32 as 2 to the 5th power. I could write 8 as 2 cubed. And then you'd leave the x on the outside here, because when you do simplify this, it becomes 2 to the 3x. Now that they have the same common base, you're only trying to solve for what that value of x is equal to. So I'm just going to circle this. You can see here that we only care about these exponents now, because they do have a common base. So 5 equals 3x. Divide by 3 on both sides. You get your exponent, right? So since 8 to the 5 over 3 equals 32, then log base 8 of the solution 32 equals that exponent. The main idea in using this method is to find a common base for each number. In this example, the common base was 2. Let's take a look at some examples. What is the value of each logarithm? So for my first step, I'm going to write this as a logarithmic equation. So I'm going to write log base 5 of 125 equals x. Remember, that x is some exponent. I'm now going to write this in exponential form. 5 to the x power equals 125. Now I'm going to look for a common base of 5 and 125. You may have guessed already that we're going to actually have a nice number here for the variable of x, but I'm just going to change it so you can see those steps. 5 to the x equals 5 to the 3rd power. Now I can match these and I can see, oh, wait a second, x is going to equal 3. So log 5, base 5 of 125 would equal 3. Now our second one, log base 4, 32 equals x. I'm going to rewrite that as 4 to the x power equals 32. Oops, sorry. Now, there are no powers from 4 raised to some power of a nice integer, a nice whole number that will equal 32, unlike this first example. So we are going to have to change this a little bit. I'm going to write this as base 2 to the x equals 2, and I believe it's 2 to the 5th power. Just had to double check that myself. So now I can see that because they have the same base, I can rewrite this as 2x equals 5. We're going to divide by 2 on both sides. X equals 5 over 2. So if I were to take this original problem, I could say log base 4 of 32 equals 5 over 2. Better yet, I could write this as, here's my little check here, 4 to the 5 over 2. Remember with our exponential, or exponents here, or with our exponent rules, I could take the square root of 4, which is 2, and then raise it to the 5th power. That would equal 32. And this one, log base 64 of 1 over 32 equals x. So I'm going to write this as 64x equals 1 over 32. This one is going to be a little challenging, right? This one's definitely a little challenging. What is that common base, right? So I'm going to actually look at my previous example. I knew 2 to the 5th was 32, so I might have to use that. If I multiplied this one again, like let's say 2 to the 6th power, I would actually get 64. So I'm going to write this as 2 to the 6th times x equals, I know 32 is 2 to the 5th. See how that's in the denominator? Well, if I want to bring this to the numerator, it's actually going to have a negative exponent. So this is going to be 2 to the negative 5. Right, with our negative exponents, it's taking the reciprocal of our numbers. See how they have a common base? 6x equals negative 5. I'm going to divide by 6 on both sides. X equals negative 5 over 6. That's how you evaluate logarithms without a calculator and by finding a common base.